Okay, what we want to be able to do here is find information about the original function using the first derivative. We want to find intervals of increasing, decreasing, and all local extrema. So step one is we need to take the derivative. So this is just going to be our power rule. So if I bring down the 3, it becomes x squared minus 1. We want to find all our critical numbers, so this does factor pretty nicely, or I can tell that my critical numbers are going to be 1 and negative 1. And we're going to create a sign chart, and I want the sign of the derivative, which is going to give me information about the original function. I'm going to split it up using my critical numbers. So if I plug in negative 2 into my derivative, so you will end up with a negative times a negative, so this is positive. So if f prime is positive, that means that the original function is increasing or going up. If I plug in 0, I get a negative number, so that means the original function is decreasing or going down. If I plug in 2 into the derivative here, this is going to be positive, so increasing. So that means that from negative infinity to negative 1 and 1 to infinity, f of x is increasing because, and this is my justification, the derivative function is positive. And then we know it's decreasing from negative 1 to 1 because f prime of x is negative. Now, local maxes and mins is where you have a critical number, 1 or negative 1, and the sign of the derivative changes, and notice the sign changes on both of them. So at negative 1, notice the sign of the derivative goes from positive to negative, so the graph goes up, increases, then decreases, so that's a local max. So I'm going to have a local max of f of negative 1, and to find f of negative 1, we are going to plug in to the original equation, right? We're always trying to find information about the original, and if I do that, I get a y value of negative 4/3, and your justification is because f prime of negative 1 was 0, and the sign of f prime of x changed from positive to negative at x equals negative 1. And then we can do the same type of justification for the local min. Notice that negative 1, it goes from positive to negative. So we would say it's a local min at f of 1. And if I plug that back into, again, the original, I'm going to get a y value of negative 2/3. And because f prime of 1 was 0, and the sign of f prime changes from negative to positive. And we can go ahead and use math symbols here. Okay, let's try the same thing with this one. Okay, step 1 is to find the derivative. And in this case, we do have to use the product rule because I have x's in both factors. So using the product rule, derivative of the first is bring down the 1/3, reduce the power by 1, times the second, plus the derivative of the second, the derivative of 8 minus x is just negative 1 times the first. Okay, now in order to find our critical numbers, we have to clean this up, simplify it. So I want it in factored form. So these are your two factors here. What I notice is there is an x to the negative 2/3, which is your GCF, that is common to both. So that is what I'm going to go ahead and take out. And then I'm also going to pull out that 1/3. I like to pull out the fractions, okay? Now, when you have fractional exponents, think about what you did when you have positive non-fractional exponents. What would the GCF between x squared and x to the 5th be? It's x squared, and then you're left with this. So we always pull out the smallest exponent. Same thing here. The negative 2/3 is the smallest. So let's see what's left over. So the 1/3 is out, this is out, so I have an 8 minus x here, plus I had a negative 1, but I pulled out a 1/3, so the only way this is going to become negative 1 here is if I have a negative 3, right? 1/3 times negative 3 leaves me with a negative 1. And then I had an x to the 1/3 here, I pulled out an x to the negative 2/3. Really, when you're factoring, remember you're dividing, so you're subtracting the exponents. So it's really 1/3 minus a negative 2/3, which becomes 3/3, which is just 1. And you can go ahead and check. If I multiply this back out, x to the negative 2/3 times x to the first will get you back to here. Now let's clean this up a little bit more. On the top, I notice I have a negative 4x plus 8. I'm going to drop that negative exponent to the bottom. So here is my simplified first derivative. Your critical numbers here is wherever the first derivative is 0. Notice if x equals 2, that will make it 0. And where also the first derivative doesn't exist. If I plug in 0, it makes the bottom 0. And 0 is a point on the original graph, so this means it's going to be like a cusp on that original graph. So here's my two critical numbers. Let's do our sign chart. Remember, the sign of the derivative is going to give me information about the original, and I always plug it back into the derivative to figure out the sign chart. Now, when you're plugging in numbers here, really the 1/3 doesn't matter. That's a positive number. The bottom number is you're going to take the cube root and square it, so this is always positive. So really, this is the only piece of the derivative that determines the sign. So if I plug in -1, that's positive, so the original graph is increasing. If I plug in 1, this is also positive, so the original graph is increasing. If I plug in 2, there's my negative, so the original graph is decreasing. So this original function is increasing from -infinity to 2 because the first derivative is positive, decreasing from 2 to infinity because first derivative is negative, and the only place where I have a sign change is 2. So we have a local max because it's going from increasing to decreasing at f of 2, and if I plug in 2 into the original function, we're going to have the cube root of 2 and then times 6. I'm going to stick the 6 on the outside here. Looks weird too. So there's my local max. If you had a calculator and punched this out, this is approximately 7.5595. Your justification, because the first derivative of 2 was 0, and the sign of f prime of x changes from positive to negative.